Welcome back to day 14 of Advent of Code. Today we shall calibrate a parabolic reflector dish. Let's dive in. We're presented with a grid of cube-shaped rocks and rounded rocks. They are presented to us as hashes and uppercase letter O, respectively. To perform the calibration of a reflector dish, we need to move the rounded rocks around by tilting the grid. If we tilt the grid up, then all rounded rocks will start stacking up north as much as they can. They will either stack against the edge of the grid, against cube-shaped rocks, or against other rounded rocks. After tilting, we can compute the total load of the rounded rocks on the support beams of the grid, which depends on the rows at which the rounded rocks end up. After tilting the grid up, what is the total load? First, let's look at this example of tilting the rocks up. Do you see how all the circles moved up as far as they can? Then once we stacked up the rocks on the north side of the grid, we can compute the load, or weight if you will. We do this by numbering the rows of the grid from the bottom up, starting at 1. In this example, the final row is row number 10. Then for every rounded rock in the row, we add the row number to the total weight. In this example, we can see 5 rocks in row 10, 2 in row 9, and so on. The total weight is 136. Now let's go on to the solution. For part 1, the solution outline is pretty short. We of course have to parse the grid. Then we tilt it and we compute the weight. Before looking at the code, let's see how the tilting algorithm works. Here is a grid with 1 cube-shaped rock and 1 rounded rock, and let's assume that we're currently processing the rounded rock. As we start on the row where the rock is located, we can then check for the row above to see if there is space to move towards. This is something we can do a few times until eventually we will see that we find a static rock. At this point, we can put the rounded rock into its new location on the grid. The nice thing is that if we process the rows from top to bottom, then we will just be able to move every rounded rock without having to worry about any potential conflicts later on. Rocks that are closest to the top, of course, always stay closest to the top compared to the rocks below them. The algorithm then looks as follows. We take in a grid, which is just a 2D list of string characters, and we shall return a new updated grid with all the rocks moved. So for every row and column, we check if the grid at that position is a rounded rock. If it is, then we store its row number in the row up variable. Then while row up is within the grid, meaning that it is larger or equal than 0, and the new grid still has an empty spot there, then we can move the rock up. Since up is at a lower index in the grid, we reduce row up by 1. At the end of the while loop, we of course place the rock. Lastly, we need to compute the weight of the rounded rocks on the grid. This can be done simply by reversing the rows and enumerating them with the start index set to 1. Then, the total weight per row is just the index multiplied by the number of rounded rocks in that row. And that was it for part 1. Let's see what part 2 has in store for us. Obviously, we aren't doing the calibration correctly. To solve this, we need to perform spin cycles. Each cycle, the platform tilts 4 times so that the rounded rocks roll north, then west, then south, and then east. And now for the most tricky part. If we perform this cycle 1 billion times, what is the total load? Here is the example from part 1 where we now performed 1 full spin cycle. So what we did is first we tilted the grid up so the rocks were aligned north, then we tilted the grid left so the rocks were aligned left, then we tilted down, and then we tilted right. In this second example, you see the result after 2 spin cycles. Do you already see how you can do this efficiently 1 billion times? 1 billion steps or spin cycles is huge. There must be some shortcut, and luckily for us there is. This problem eventually stabilizes into a repeating pattern of grids. Thus the problem reduces to us finding this cycle. The outline then changes, and we will try to find a cycle based on the input grid. From this function, we get back some grid state, the spin index at which we found the cycle, and the length of the cycle itself. Once we have this data, we can finish the spin cycles efficiently using the finish function, which gives us our final grid. On the final grid, we of course compute the weight again. But how does finding the cycle work? First, assume that this bars represents all the steps that we need to take to iterate from spin number 1 to spin number 1 billion. Then what we can do is to start simulating the spin cycles. At some point, we will find that we encounter a grid state which we've already seen. And this is a key indicator of having found the cycle. The cycle here is indicated as the green segment. Note that the blue segment doesn't necessarily overlap in terms of states with any of the states within the cycle. There can be, and there are, some amount steps that eventually cause us to get into the stable pattern, which is our cycle. From this point, we can skip forward, as we know the cycle will repeat indefinitely. We don't have to loop through our cycle of grids over and over again. The pink segment on the tail end is the part where we figure out the number of steps that still need to be done to get to 1 billion steps. This is needed because our green segments won't make us end up perfectly on the 1 billion step mark. Before looking at the code to find the cycle, we need two supporting functions. These functions allow us to rotate and tilt the grid. Note that rotating the grid allows us to tilt the grid in the 4 directions, while not providing any code to tilt specifically in any of the wind directions. We always tilt up but just rotate the grid instead. Then, finding the cycle works as follows. We can make the grid hashable via the stringify, which just turns back the grid as one big string. This string can be stored in a dictionary, which we shall call grids. Then we start on index 1 and we will iterate until we find a cycle. So we update the grid and perform one spin cycle, and we hash the resulting grid. If that hash is in the grids map, then we have seen it before and we found our cycle. If it's not in there, then we simply add it and continue. The cycle length which we return is the current index, meaning it is our current spin number, minus the previous index at which we've seen this state of the grid. Then finally, given the endpoint of the cycle and the cycle length, we can extrapolate and finish the remaining spin cycles. So first, we find the number of spins remaining, and then we check how many full cycles fit into there. We subtract those cycles, and while we have spins remaining, we perform another cycle. Eventually, we return the final grid. And that was it for today. Again, 2 more stars on a very interesting problem. Thank you for watching, and until the next one.